Hello, geometry students, and welcome to a new unit. We are starting unit 4, all about quadrilaterals, but we focus the first few days on just polygons in general. So this first page here has a great little reference for when we get into the bulk of talking about all the specific quadrilaterals that we'll learn within the unit. So just a nice little reference to have. A quick overview of kind of what's coming. So today, like I mentioned, we're going to start with polygons and specifically their angle sums. And you can see that we break up when we do have a quiz in this first unit before we finally hit the test here. But notice, proofs. They're going to keep on coming. So unit 3 was just the start of proofs. We will continue to see proofs kind of dispersed throughout the units of the year. Because we're back into some algebraic stuff, you are going to want your calculator today. So if you don't have it nearby, maybe go quick grab that. You can pause the video if you need to. Otherwise, let's get going here. So when it's saying properties of polygons, a couple of things. There's vocab listed here. So any corner point we refer to as a vertex. If we're talking plural, it's vertices. And then a diagonal, anything that you connect from one corner to another that's on the interior of the picture itself. And then obviously, sides. So over here, you have a cute little chart to reference based on number of sides and what the name of the polygon is. I know you know triangle. Quadrilateral probably sounds pretty familiar too. As for the rest of them, they should sound familiar, but you do need to familiarize yourself, if they are not familiar, with the rest of them. So like hexagon for 6 sides. You got a heptagon, can also be called a septagon for 7 sides. And then octagon, nonagon, decagon. Nonagon's my favorite because it sounds a little goofy. And then dodecagon. There are names for polygons beyond that, but we will refer to them as n-gons. So what I mean by that is if there's 15 sides, we'll just call it a 15-gon and literally write the number 15-gon. All right. So you don't have to worry about any vocab beyond a dodecagon. So with the first ones, all they're asking you to do here is it's saying that a polygon is described as a closed figure, meaning that it's not like left open, all the segments connect, formed by 3 or more segments that intersect only at the endpoint. So they don't like crisscross in the middle or anything. So when it says tell whether or not the figure is a polygon and then name it by the number of sides, well, the very first one, that's a really great example of a polygon because everything's connected. And so if we count, we have 1, 2, 3, 4, 5, 6. So we would say, yes, it's a polygon. And specifically, it's a hexagon. For number 2, they're all straight line segments. They're all connected. Therefore, it's closed, right? And so again, yeah, this is definitely a polygon, even though it looks kind of like just an arrow. But if you count, you got 1, 2, 3, 4, 5, 6, 7. And so if you look at your list, that can be a heptagon, or I mentioned above, a septagon. You can say it either way, right? For number 3, even though it's a closed figure, those aren't straight line segments. So yes, it's a cute little, sliver of a moon, I guess, but no, it's not a polygon, right? And then for number 4, this one is another one that we would say no to because it's open at the top. So it's not a closed figure. All right, on to that next page. Whoops. Let's take a look here. So regular polygon. We have actually talked about how to construct a regular hexagon earlier this year. So you may remember that terminology. Regular just means that all the sides are congruent and all the angles are congruent. So sometimes when it's a regular polygon, it's got a nice pretty name to it. So like a regular triangle, if I think about those 3 sides being the same, would be an equilateral triangle. If I think about a quadrilateral that has all the sides and the angles the same, we wouldn't call it a regular quadrilateral. We'd refer to that as a square. Right? As we get into the polygons with more sides, there's typically not nice names to go with it. So that's why we just use the term regular. As for concave, versus convex, I was thinking concavity. It's a concave if any part of the diagonal is on the exterior. So what I mean by that, if I were to grab, maybe I'll grab a red pen here. If I was to connect this vertex to this vertex, that diagonal would fall outside of the diagram. And so if it falls on the outside, that's how I know that it would be called concave. Or you can think it has it like caved in on itself, right? So the diagonal's on the outside here. And then as for convex, that's typically what you would picture. If I said, like, draw me a quadrilateral, you probably would draw something like this versus this, because this is 1, 2, 3, 4 sides, but this is typically what we think of. So convex, no diagonal contains any points on the exterior. So if you were to draw the diagonal here, it would be contained completely within the figure, right? So the diagonal's on the inside. All right, so at the bottom, you have 3 little examples here. It says tell whether or not it's regular or irregular, right? And then tell whether it's concave or convex. So basically, if it's not regular, then we would classify it as irregular. So if you look at each one, regular means all the sides are the same, all the angles are the same. So if we look at it here, they're clearly showing you by 1 stripe and 2 stripes that not all the sides are the same. So this would not be regular. This one should be irregular. For this one, all the sides are the same. And if we look, all the angles are the same. So this would be regular. So keep in mind, even though all the angles were the same, the sides weren't. That's where the irregular part comes in. For this one, all of those little sides, it kind of looks like a little star, are exactly the same. But if you look at the angles, they've only got 4 angles marked. And there's 8 sides, which means there's 8 angles. The other angles are these ones here, here, and here, which are very obviously not the same as those little acute angles there. So this one would be irregular. And in case you need to write yourself a note as to like why not, it was because not all the angles are the same. Whereas this one was not all the sides. And then as for the concave versus convex, all right, concave versus convex, if you were to draw on a diagonal, does it fall on the inside? Absolutely. So this one would be convex. Draw on any diagonal, it would all be on the inside, so convex. If I draw a diagonal here, here's one that would fall on the outside. This would be considered concave. So sometimes it helps to see a couple examples to be able to compare the differences there. All right, now we have some formulas to get into. Flip on over to that next page here. So the sum of the interior angles. We sort of use this little chart to kind of build up a pattern of what's going on here. So for each one, you've got a triangle, quadrilateral, pentagon, hexagon, and then it kind of jumps to an n-gon. We'll talk about that at the end here. They've got a diagram for you, which is helpful. So the first part, when it asks you, what is the number of sides? Okay, easy peasy. Triangle, we got 3 sides. Quadrilaterals, 4. Pentagons, 5. Hexagons, 6. When it says, what's the number of triangles? Okay, well, in a triangle, there's simply 1 triangle. To answer it for the rest of these, I want you to choose 1 corner point and draw in all the diagonals you can from that 1 corner point. So like, let's say I picked this like bottom left corner point. The only diagonal that I can draw is the one that goes from here to that opposite corner there. In that case, I've created now 1, 2 triangles. So there would be 2 distinct triangles in the picture. Right. For the pentagon, do the same thing. Pick 1 corner and draw on the diagonals. So here I can draw in 1, 2 diagonals. And now I've created 1, 2, 3 triangles. And then if you do the same thing for a hexagon, and it doesn't matter what corner you pick. You could pick up here, any of them. If I draw on the diagonal, I've got 1, 2, 3 diagonals I can draw in, which creates 1, 2, 3, 4 triangles. So you're probably starting to see a pattern. The number of sides goes 3, 4, 5, 6. The number of triangles, 1, 2, 3, 4. When it asks for the sum of the interior angles, I know that you know the answer to this one because we've used it this year. The angles in a triangle add up to 180 degrees. Mm-hmm. Everything beyond that is based on this. So for a quadrilateral, that might be another one that you know. Like if you think of a square, those 4 angles add up to 360. Or the other way you can think of it is you have 2 triangles. So if I kind of highlight the corner angles of my triangles, altogether, they create the 1, 2, 3, 4 corners of my quadrilateral. And so 2 triangles together, 2 180s, turns into that 360. I can use the same argument here. If I look at all the corners of the triangles, so there's the corners of one. Here are the corners of the next one. There's the 3 corners of the last one. All together make up those 5 angles here. So if I have 3 triangles, then I really have 3 times 180. And if you grab your calculator, here's where it starts to come in handy. That's going to give me 540. So some of you might be like, I think I knew that. Awesome. If not, well, here's some new fun facts for you. So what I want you to do right now is think about, if I have 4 triangles, what should the total angles add up to? Well, 180 for each triangle times 4. If I do 4 times 180, that's going to come out with 720. So if you add up all the angle measures just in the corners of the hexagon, it should equal 720 degrees. So you can see it's going up by 180 each time. Or in a generic way to do it, I'm not going to draw a picture, but I can say that the number of sides, that would be n itself. The number of triangles, well, take a look. To go from this column to this column, the pattern, so here's 3 and you had 1 triangle, 4 and you had 2 triangles, 5 you had 3 triangles. This number is always 2 less than whatever was here. So this would be n minus 2. And then over here, we said it's the number of sides, or excuse me, let me adjust that, the number of triangles times 180 degrees. So if I can think of it as the number of triangles times 180, then what we can do is we can actually write that as n minus 2 and then times 180. Now it looks a little weird to put the 180 at the end, so I'm going to flip it around. So when it says the formula for the sum of the interior angles, it's always 180 degrees times the number of sides minus 2. So n is equal to the number of sides in the polygon. All right. And it's because that fun little pattern of how many triangles you can fit in there. Now, when it says, what's the formula for a single interior angle in a regular polygon? It's the idea that if you take the sum and you divide it by however many angles there are, you can calculate one little corner all by itself, like one little angle here. So all you'd have to do is take the sum and divide it by how many angles there are. So you would take the sum of 180 times n minus 2 and divide it by however many angles. Well, if there's n number of sides, there's also n number of angles. So you would divide it by n. All right, there are your first 2 formulas. So if I'm looking just for the sum, 180 times n minus 2, if I want a single angle, and it has to be specifically for a regular polygon, and that's because all the angles are equal, then you would take that sum and divide it by n. All right. When you flip on over on the next page, there's some space for some practice here. So over here, when it says, let's find the sum of the interior angle measures of a regular octagon. Well, you've got a diagram, but right now I'm hoping that you're thinking octagon. Okay, that's 8 sides, or you can count up and confirm that. So again, the sum formula, I'm just going to write it down again. The sum formula is equal to 180 times n minus 2. So we just plug in 8 here and then calculate. If you want to, you could always do 8 minus 2 and get 6 first and then go to your calculator. But otherwise, 180 and then times 6, that's going to give us 1,080 degrees. So if you add up all those angles, which should make sense if you look at them, they're all obtuse. That's going to be a pretty big number when you add them all up. All right. When it says find the measure of each interior angle, if it's a regular octagon, now you can take the sum and divide it by the number of angles, which should be 8. So if we do 1,080 divided by 8, again, grab your calculator. That's going to come out to be 135 degrees apiece. So each one of these, if this is a regular octagon, should be 135 degrees. All right. For the next one, it says find the sum of the interior angle measures of a regular pentagon. So pentagon, you got n equals 5. I want you guys to try number 2 on your own here. All right, so feel free to pause the video, give them a try right here. You're going to be answering your post-video question based on number 2. So try part A, try part B. If you're not totally certain, go back and look at what we did in number 1. Right. Number 3 is a little bit different, so I'd like to do 3 with you. 3 says name the polygon whose interior angles have a sum of 1,260 degrees. So they're giving you the sum. And if it's asking you to name the polygon, then what we really need to do is we need to find how many sides there are or solve for n, all right? And if I can figure out like, all right, n is 10, then I can name it a decagon or whatever it might be. So let's write the formula down first. The sum is equal to 180 times n minus 2. And now this 1260 goes in on the left-hand side here. So we have 1260 equals 180 times n minus 2. There's 2 ways you can proceed from here. We can distribute that 180 through, which is usually the way that I think to do it first, which would give me 180n. 180 times 2 is going to give me 360. And then you can continue by adding 360 to both sides. So on your calculator, I'll bring mine on over here. 1260 plus 360 brings us up to 1620. And then finish it out by dividing by 180. So divide by 180, and it comes out as 9. So to name the polygon, if it's got 9 sides, here's my favorite one. It is a nonagon. All right. Now, if it didn't have a nice name, you would just say an n-gon, or not an n, but like if there wasn't a name here, you'd say a 9-gon, which sounds weird, but so does nonagon. All right. For number 4, let's save this guy for a little recap for class. All right. You got one more page to look at. Flip it on over. All right. So number 2 you did on your own. Number 4 we're going to do together the next time we see each other. Let's do number 5. All right. On number 5, find the measure of each angle in the polygon shown here. All right. So if I have to find the measure of each angle, we can kind of already tell. You're going to have to figure out what this little a is. So that's the variable here. So we got to find a before we can do that. To be able to set up an equation, typically if this was a triangle, we'd add up the angles, set it equal to 180. Well, in this case, you need to find what the sum should be first. So we got to find the interior angle sum first. All right, so we've got 1, 2, 3, 4, 5, 6 angles or 6 sides. And so since this is 6-sided, we got a hexagon here. Now, we already calculated the sum for hexagon, so you can flip back and take a look in your notes if you'd rather. Otherwise, if it was a sum that we didn't know, we'd take a quick pit stop here and say, okay, let's do 180 times 6 minus 2, and that would turn into 180 times 4, which would give us 720. Now I know what all of those angles should add up to, and I can set up an equation to now solve for A. So I'm going to go in alphabetical order so I don't lose track of anything. I got 2A plus 5A plus 4A plus another 5A plus 3A, and then finally one last 5A. All of that should add up to 720 degrees. All right. Combining all of these guys, they're all like terms. So 2 plus 5 plus 4 plus 5 plus 3 plus 5 all together should be 24A equals 720. Divide by 24. So if you grab your calculator, 720 divided by 24, we get a nice pretty value of A equals 30. Now, sometimes the question will just say find A and you're done. This one said find each angle. So you're just doing a quick plug in to finish it. So angle A was 2 times A, so 2 times 30 would give us 60. Angle B, angle D, and angle F were all 5A, so I can kind of do that at once. Those all come out to be 150 degrees. And then the last ones are angle C, which is 4 times 30, is 120 degrees. And angle E was 3 times 30. Ooh, comes out at a perfect 90, a nice right angle right there. So there's your answer to the question. Number 6, we're going to save that for a recap in class. So lots to do next time I see you. And then at the very bottom of the page, if you'd like, you can fill in the formulas one last time. What's the sum? And then what's the measure of a single angle, where you then add the divided by n piece of it. All right. Please go answer that post-video question. Thanks so much for watching, guys.